Welcome to Autumn Math. In this edition of Autumn Math, we're going to talk about evaluating and graphing log functions. All right, so let's talk about some of the purposes of logs. So I've mentioned before that one of the purposes of logs is to find the value of an unknown as an exponent. And when you have the case of 2 to the x is equal to 4, it's pretty straightforward. And probably intuitively you can say that x is equal to 2. But what about when you have 5 to the power of x is equal to 30? Well, we know that 5 squared is equal to 25, and we know that 5 cubed is equal to 125. So we know that x is going to be between 2 and 3. But can we find an exact value just from looking at this? And the answer is no. You're going to need to use logs in order to find the value of this unknown as an exponent, when the answer is not so intuitive. The other purpose for logs is to be able to evaluate fairly large numbers, and we'll do some of that practice when we get to the later chapters. All right, so I like to bring things down a level and talk about the different forms of writing expressions, one in exponential form and one in log form. And log form is just another way to rewrite exponential form. And so what I've done is I've drawn a paper. Now we're going to use papers in exponential form, and then we're going to rewrite them in log form, just so you get used to the idea of the pattern. So it's like two languages, one way to say something and another way to say the same thing, written in two different ways, but they mean the same thing. So in exponential form, using the symbols, we have a house to the power of a sun is equal to the heart, or is equal to a heart. In log form, it's log base house of heart is equal to sun. Right? So we're just moving the symbols around as we express both exponential form and log form, but they mean the same thing. Right, so I have an example here. It looks like some type of animal. It's a cat to the power of a dollar sign is equal to the flower, and if I wanted to rewrite that in log form, it'd be log base cat of flower is equal to the dollar sign. Right, so it's very important that when you're writing the values, that one, you write them in the proper location, and two, that you express both exponential and log form properly. So in exponential form, in the top, I have a to the power of x is equal to y. You notice that a is on top of the line, x is above the line, and y is on top of the line. And if I were to rewrite this value in exponential form, I would say log base a of y is equal to x. So now you have to be careful, because this a is actually on the line, not on top of the line. And y is now on top of the line, and x is on top of the line. So things get confusing when the a starts shifting up and goes on top of the line instead of directly on the line, because you can write log with a base of 10 of a to the power of y is equal to x, and that means something entirely different. So that base value has to go on the line, and then of the y value goes on top of the line, and then the exponent here goes on top of the line. So be careful about how you write the values in log expression. In log form, the base needs to be right on the line. Okay, so again, two different ways to express the same thing, stated differently, written a little bit differently, but again, they mean or asking for you to evaluate the same equation. All right, so again, here we go with symbols. I want you to take exponential form, convert it to log form, and then log form to exponential form. I'm going to take a break while you rewrite those, and let's get back together. All right, so in exponential form, I have house to the power of a flower is equal to the heart. Log form, log base house of flower is equal, log base house of heart is equal to flower. And then in log form, we had log base star of rectangle is equal to heart. And in exponential form, it's star to the power of the heart is equal to the rectangle. All right, so you can rewrite this in log form just for fun if you want. I'll show you the answer. So we have some animal to the power of some funky guy with hair is equal to a cat that says woof. And then log to some log base some animal saying woof is equal to the funky guys with the different hair. Anyway, you get the idea. We're just having fun. All right, so part of the assignment for you was to create 3 symbol relationships in exponential and log form and to pass that into me. All right, so moving on now. Now we're going to start using values, numerical values, and express those in log form and exponential form. So log base 7 on the line of 49 on top of the line is equal to 2. And rewritten in exponential form, 7 to the power of 2 is equal to 49. So in academic language, we have some log basics. Log base b of y is equal to x is the same as b to the x is equal to y. Log base b of y is equal to x is described as log base b of y is equal to x. Logs are generally used to determine the value of a variable as an exponent or unknown as an exponent. As we gave the example 5 to the power of x is equal to 25 is easy. X is equal to 2, but what about 5 to the power of x is equal to 39? Log base b of y is equal to x is in log form. B to the x is equal to y is in exponential form. So you need to be fluent at going back and forth between log form and exponential form. All right, so we're going to ask you, in order to increase that fluency, I'm going to ask you to take these equations in log form and rewrite them in exponential form. There's really nothing to solve, you're just rewriting. I'm going to pause here. Okay, log base 4 of 16 is equal to 2 is the same as 4 squared is equal to 16. You can pause and read the balance of the answers. Right now I'm going to ask you to move in the other direction. We're taking exponential form and moving to log form. I'm going to pause here while you write the answers. Right, log base 5 of 25 is equal to 2 is the same as 5 squared is equal to 25. You can review the balance of the answers here and check your work. All right, so now we're going to talk about spiral logs. First is a common log, and a common log is just a log with a base of 10. As with some value, sometimes when you have a coefficient of 1, you don't state the 1. Just as with a common log, if there's no base stated, then you can assume it's a base of 10. So common log is a log with a base of 10. Example would be log base 10 of y is equal to x. It can be simply written as log of y is equal to x. Natural log has a log with a base of e. So log base e of y is equal to x can be and should be written as ln y is equal to x. And you would express this as natural log of y is equal to x. So whenever you have a base of e for a log, you're going to rewrite that as ln instead of log with a base of e. So log base e of y is equal to x is the same as natural log of y is equal to x. In exponential form, we're going to rewrite that as e to the power of x is equal to y. All right, so now I want you to write each equation in exponential form. I'm going to pause here. All right, so common log, the base is not stated, so we assume it's 10. 10 to the power of 1.6 is equal to 40. Natural log, base of e, log of the base of e, so e to the negative 1.6 is equal to 0.2. You can read the rest of the answers and check your work. Right, so now we're going to go in the other direction. Rewrite exponential equation in log form. And you get natural log base e of 7.4 is equal to 2. Read as natural log of 7.4 is equal to 2. Log of 1,000 is equal to 3. Natural log of 7 is equal to x. Log of y is equal to x. All right, we're going to move on. You can check your work and pause if you'd like. All right, so I want you to solve for these values without using a calculator. I'm going to pause here while you do that. Right, and the first one is just 10 to the power of 3 is equal to 1,000. Second, 6 to the power of 2 is equal to 36. Third one and fourth one are getting a little bit more tricky. 5 to the power of 0 is equal to log base 3 of x. 5 to the power of 0 is equal to 1. So then rewritten in exponential form, 3 to the power of 1 is equal to x. And you'll see that as you start solving log equations, you'll need to convert back and forth between exponential and log form. That's what we did here in order to solve for x. And the fourth, natural log of x minus 2 is equal to 1. Rewritten in exponential form, e to the power of 1 is equal to x minus 2. And then x is equal to e plus 2. Now you have to be careful because this parentheses can mean something else if you take off the parentheses. So natural log of x minus 2 is equal to 1 is the same as natural log of x is equal to 3 is the same as e to the power of 3 is equal to x. So you can see that these two values are not the same, and that the end parentheses or parentheses of this value here is important as you evaluate any log equation. All right, so we're going to move on from this. All right, graphing logs. I have a table here for you. You're going to fill out this graph while I pause for a moment. And then you're going to create two separate graphs based on the table. All right, so you're going to fill out the table, and these are the values you should get. And you should recognize that this is just an exponential decay function when I have a b value of 1/2. So remember, y is equal to a times b to the power of x, where b is between 0 and 1. You end up with an exponential decay function, and when it's greater than 1, you end up with a function that's growth function. So you can see here we've just converted our growth and decay functions from exponential form to log form. All right, so exponential form, graphing log equations, b is greater than 1. In this case, b is 2. You can see that's exponential growth. In this case, we had b is equal to 1/2. These are approximate rough values. We have a decay curve. Okay, now I want you to change the x and y. So we've just swapped the location of x and y. Previously we had y in that location and x in this location. So now I want you to swap those values, and now we're going to take the value of y, right, and then we are going to solve for x. So 1/2 to the negative 3 is equal to the x value, and you're going to write those values in to the spaces here. I'm going to pause, and then we're going to graph those. All right, you're going to end up with the same values, but now we've flipped the values for x and y. And essentially what you've done is you've created an inverse log function. Right, so if you were to plot these values in the inverse log function, you should end up with something that looks like the blue line. So we're going to compare them with the red line, which was the previous function with exponential growth. Now we've graphed the inverse log function, and both values where b was equal to 2 and b was equal to 1/2. And you can see that they're symmetric, or they're reflected over the y is equal to x-axis. You can also see that the domain and range values have basically also been flipped or switched as well. In the prior example where we were dealing with exponential growth and decay and not the inverse of the log function, we had the domain was all real numbers and the range was y had to be greater than 0. In the inverse log functions now, we flip the domain and range. Domain x is greater than 0. As you can see, x never gets to be less than 0, and y would be all real numbers. All right, so just evaluating your growth and decay functions in log form versus exponential form, and then finding the inverse log functions as they relate to the growth and decay functions for both values that are greater than 1 and between 0 and 1. Right, so that's it for this edition of Untitled Math. Hope you enjoyed that quick lesson on exponential log form and then graphing exponential and growth and decay functions using the log form, and then the inverse log functions. Hope you join us next time, next edition of Untitled Math.